The thermal noise in MOS transistor can be modeled between drain and source with the noise current density is 4kT gamma GM. Here the gamma is approximately 2/3 in long channel device, and the short channel device is getting larger and larger, like it's approaching to 3/2 in long channel device. So it's getting larger in short channel device, larger in deep submicron. Each small signal model can be shown on the right. It is more in detail. Here the typical transconductance GM times VGS and output resistance, and we add that the noise thermal noise current like that. On top of that, we have a gate register. Out of the gate poly register, this is coming out of poly register, gate poly register, that also noise contributor. So we have a register and register noise. So for the gate register, we have a 4kT R noise voltage density, and for the current noise, we have a current noise density 4kT gamma GM. Right? For the practical noise flows for the given bias, noise current flow between drain and source. So this kind of a thing can be equivalent. We can draw the equivalent circuit. In some case, it is easier to consider this kind of a model. So this is the equivalent. We add that noise voltage source to create the same amount of noise. That would be what? See, since we know the transconductance GM, that would be IN square over GM square. That is what? This value is 4kT gamma over GM. That is Vn square expectation, right? So this is the another way of representing the most thermal noise, either in current source or voltage source. If you remember the register case, the register noise can be modeled either voltage or current source, right? So for the voltage source, we know that 4kT R is the noise voltage noise voltage density, and noise current density would be Yn would be Vn square R square. That would be 4kT over R, right? So this is a similar derivation. So we have either consider that or the other way. Okay. If you look at the physical layout of the transistor, we can draw like that. For example, the poly register is quite large if you use a single poly like that, right? And also we have a drain and source diffusion register, right? Diffusion area, it also has finite resistance. So we can model those gate and source and drain side register. All those are noisy sources. So one way to reduce gate poly register is that we draw that in parallel, right? Making drawing parallel, like on the right hand side, parallel connection. So we split that transistor into two, for example, using the two finger device like that. That would reduce the amount of poly resistor, right? On the left hand side, this register is a distributed register. You may consider that small transistor in parallel like that. So all these RG1, each subsection distributed register RG1 and 2 and 3 and N, like all those are in series. So overall gate poly resistor is in series like that, right? So to avoid that, we can have either two-way. One is the both sides of the edge is using the metal connection. We can use the poly distributed resistor value, or you can split like into two devices and make it in parallel resistor connection, right? Okay. More extensive reduction technique, poly resistor reduction technique, is both 1 and 2 technique, right? So you tie the poly with the metal at both edges, and also use multiple fingers, right? We have multiple finger connection, right? So this is typically used in RF device to minimize the noise sources. This is the typical RF device layout, okay? For the MMOS, we always put a substrate contact nearby, but each channel is quite far away. So between this substrate contact and channel, we have a substrate resistor here, like that. The substrate resistor is also to the bottom. That is also tied that to ground. So this kind of a distributed substrate resistor is there. So this kind of thing is modeled in RF device. For typical regular devices, those are not modeled properly. So what we have to do is to place the substrate contact nearby, as near as possible, to minimize the substrate resistor effect, and also or surround the device with the substrate contact. Put a substrate contact, right, and put a circular substrate contact around the device. That would reduce the substrate resistor problem, right? Typically this happen in RF device or sensitive device case, okay? In most transistor, we have a flicker noise on top of a thermal noise. This is a silicon crystal between silicon dioxide and the channel surface. There's some dangling bonds here because of different material there, so there's some broken bonds there. So in this dangling bonds, as the electron or mobile carrier moves along the silicon crystal, it may trap on or released, right? So this kind of a trapping and release the event happen randomly. So this kind of thing causes flicker noise. As a flicker noise, voltage density along the frequency is like this. So K is some proportionality factor, divide over COXWL. This is the area of the device, and this is a frequency. So we have a frequency here. So Vn square, it will goes like down like a 10 dB per decade. Decade slope is there. So if you're with the thermal noise overall, this is the thermal noise level, thermal noise. This is thermal noise and flicker noise. So the typically low frequency is dominated by the flicker noise. And this point is called the flicker noise corner. So this point is where the amount of flicker noise and amount of thermal noise are equal. So flicker noise corner is defined by like that. So what we can do for reducing flicker noise is to making large area. If you make a large area, this kind of trapping and releasing mobile carrier thing is kind of averaged. So we have averaged trapping and releasing action will result in the lower noise. So for the same kind of a flicker for the device, if you draw much larger, then the electron movement random movement nearby this kind of a surface area, as somehow the averaged and it gets less noise. Okay, W times L, this is W and L and L and W. Let's say M times W, right? So if you make it M times larger device, so area is M square times area, meaning M square lower flicker noise power. So if you make it double, for example, if you make it double for all the dimension, so it becomes a 4x large area. In that case, we have a 4x lower the noise power. So in terms of RMS voltage, it becomes a 2x lower RMS voltage. So to get the 2x lower RMS voltage, noise voltage, 4x larger area is required. Okay. So the flicker noise has a minus 10 dB per decade slope, and the thermal noise is flat. So if you add those two, we have a corner that is the 1 over f corner is defined by here having same flicker noise and thermal noise. This flicker noise corner can be something to consider, is that if you have a larger flicker noise for the given thermal noise, you will get the larger flicker noise corner. On the other case, for the same flicker noise, if you have a larger and smaller thermal noise, then you can have a larger flicker and smaller flicker corner. So having just specifying flicker noise corner is large or small, that doesn't necessarily result in lower flicker noise, because just the flicker noise corner can get larger even for the same flicker noise if the thermal noise level is getting large. Okay, so you have to look at both thermal and flicker noise when you consider the noise. Okay. one thing to consider is that for the flicker noise corner is proportional to area, inversely proportional to area, so 1 over WL. But for the white noise level is inversely white noise level is inversely proportional to GM, because the VN thermal white noise device VN square is that 4KT over GM, right? So this is approximately proportional to L over W. So if you have a smaller L, you get the lower noise, and large W, then you get the lower noise typically. So what you can do for reducing both flicker noise and white noise is that first you have to make it large area, and then try to reduce the L compared to, so you try to use small L and large W, right? In that way we can maximize the GM. So for a certain circuit, you probably want for a certain GM, so you want to first implement the GM, and then once you get the proper GM, you can play with the W and L to get the desired flicker noise level. Okay. So again, the first step is design GM. Second, once the GM is defined, the white noise level is defined, right? Third, once the desired white noise level is determined, then change the increase WL times L without changing without changing what? GM. So how we can increase the area without changing GM is that, so for example, for device like we have a W over L that resulted in the GM, desired GM, then you can multiply like a 10W and 10L, right? Like that. Or right, you can just scale up, right? Scale up the device, to scale up. Okay. Let's consider the amplifier noise. The most simple amplifier stage using a single transistor shown in here, that is as a source, common source amplifier. We have a single noise source, that is M1. It's between drain and source. We have a current noise. Its power density is 4KT. Current density is 4KT gamma GM. In that case, what would be the output noise voltage? Voltage noise density. So because using the circuit analysis, we have a finite RO there. So once we plug the gate to AC ground, all the noise current will flow through what? RO. So if we end out for the given noise, so we can say that RO times minus IN, right? So since we don't know the exact magnitude of the IN, what we know is the expectation of the noise current density scale, and so we know the mean scale and current. So we can do the similar, take the scale and take the expectation, take it scale, expectation of all. So we know that R0 scale, so all register and currents are not correlated, so we can take it out. So IN scale. So IN scale is what? We know that for KT gamma GM. So overall output noise voltage current noise voltage density, noise voltage density is found by like that. So right. As I explained before, this kind of a noise current source can be found also. We can draw that equivalent network like this. So its input side is Vn scale is for KT gamma over GM, right? In that case, output noise voltage is that what? The same as like here. We know that output AV gain is GM times RO. So Vn out scale expectation is what? AV scale times Vn scale expectation. So that would result in what? GM scale RO scale times 4KT gamma over GM. That is exactly same as before, right? 4KT gamma GM RO scale. Okay, this is the equivalent circuit. So once we take out this kind of the noise current or voltage, this transistor now become noiseless. We are assuming that this is noiseless because all the noise are lumped on the IN here on the right, or the voltage source on the here, right? So far we just assume that the thermal noise present. What about the flicker noise? Flicker noise, what is the flicker noise component? In the previous example, our flicker noise model was modeled at the gate, 1 over F flicker noise. So Vn 1 over F scale flicker noise, what? K over COX times W times L times 1 over F, like that. So if you move that to current representation, that would be Vn 1 over F scale times what? GM scale, right? So that would be K over COX W times L 1 on GM scale times 1 over F, right? So do not be confused with the flicker noise. Here we have written, we have found with the voltage source at the gate in series. So noise voltage was that. So we have to convert that into current, noise voltage current in that case. Okay. So finally, considering noise voltage at the output would be IN scale times RO scale T gamma GM plus K over COX W times L GM scale 1 over F. Okay. So far we just were able to find the output noise voltage. We have to think about the in general case. We have a circuit. Inside the circuit, many noise sources are there. So we may monitor noise voltage at the output, right? So what would be the right way to specify the noise? We just having large output, having the output noise would be enough. That would not be true, because the following reason we will see what we can do. And so that's why for the typically noise representation, we find that the input referred noise, meaning we have many noise sources like that, we find the equivalent. So this circuit is noise free circuit. All the noise is lumped on at the input referred noise, either voltage noise source or current noise source. So having like this kind of a finding this equivalent input referred noise, we can monitor the same output noise voltage, right? So why we are doing this, we will see later why we have to do it like this. Okay, let's calculate the output noise for the common source amplifier shown here. We have a resistive load there. Resistor has the noise current here, and also thermal noise from the MOS transistor. We have two noise sources. So considering that, we have all the noise will flow through the RD, assuming RO is infinity. So we have overall output noise voltage would be 4kT gamma GM, and flicker noise and 4kT over RD times RD square. So in this case, we know the circuit gain is AV is the GM times RG, right? So if the GM times RD is, for example, large, if the gain is large, for example, large RD, will get the large, for example, large RD, large GM, and RD results in large AV. That results in what? Large output, large VN out scale. So our conclusion would be what? So do we have to reduce the GM or RD? But that will result in smaller gain. So do we have to implement minimum gain or small gain? This is the amplifier. We want to add the signal and amplify, right? But by the action of the amplification, if you have a large gain, you get the larger noise at the output. So this is something not properly representing the circuit noise. This kind of misleads us to we have to reduce the gain, but actually not. So what we have to care about is that SNR, signal to noise ratio. So if the signal get larger and smaller, for example, even with the larger noise, if the SNR improves, right, the noise is small, right, the large gain and small AV, right, even though the noise is larger than before, if the signal is much greater than small gain case, then SNR improves, right? So this is the small gain, SNR goes down. So what we have to see is there's some kind of SNR perspective. We have to look at the circuit. So we need to quantify the circuit noise regardless of the circuit gain. So that's why we are delivering the concept using the concept input reference noise. So how we get the input reference noise? First, we get the output total noise that is referred to the input by the gain, circuit gain, what? AV square. So input reference noise, input reference noise voltage would be Vn out square divided by circuit gain. Then what we get is that gain is what? Gm square times Rd square and Vn out square. So we use that input reference noise voltage. In that case, for any circuit, you would assume the same input signal size, right? For the output side, output signal depends on the circuit gain. But if you move that noise onto the input side, we can easily compare with the same input signal. We can look at we can see that how large the noise voltage is there. In this case, if the noise is smaller, then your circuit has high SNI, meaning low noise, right? So we have to, when you compare different circuits with a different gain, it is more meaningful to compare the input reference noise voltage or noise current. So that's why we are introducing the input reference noise concept here. Okay. Input reference noise concept can be considered like this. On the left hand side, we have a noisy circuit. Inside the circuit, we have a variety of noise sources that results in the output noise voltage. We can measure the output noise voltage by applying the input zero input and then measure the output voltage. So now we think of the fictitious noiseless circuit inside. We don't have any noise source. All the noise are lumped into input noise voltage like this. We find that noise voltage, lumped input noise voltage, that results in the same output noise, Vn out. Then we say that Vn in is input reference noise. So for both left and right models, the same output noise is monitored at the output. So mathematically, those are equivalent. So our question or work to do is to find this input reference noise that capture all the inside of the circuit noise, right? So once we find that input reference circuit noise for different type of a circuit, we can easily compare noise level. So we can it becomes now easy or convenient to compare noise of the circuit regardless of a circuit gain, right? We don't care about the circuit gain, whether that is 10 or 100. What we see or what we care is at the input side noise voltage, input reference noise voltage. If this input reference noise voltage is larger or smaller, then we can say that this is low noise or large noise. Okay. Let's take a look at the common source amplifier shown on the left again. So we know that this gain of this amplifier AV equals GM times F loop gain GM times RD. Right? If you calculate the output noise, then when the input is tied to ground, then we can find that 4kT gamma GM out of M1 here, and the register and also flicker noise component here, and the register noise from the register, we have a 4kT over RD. This is the output total IN out square, and times all these noise current source are flowing onto the RD register, right? So overall output noise voltage can be found like this. Now, if you want to calculate the input reference noise voltage, then we have to divide Vn out square by the voltage gain square, right? If that is the case, now we put this gain, divide that with the GM square RD square, then finally input reference noise voltage like this. What we can see is that if you want to reduce the input reference noise, right, to reduce input reference noise, what we can do, noise Vn in, then what we can do is that GM must be large, right? If you have a large GM, your input reference noise is smaller, right? And also if you have a RD is large, right, meaning you get the also smaller gain. So that results in what? So if you have a large AV, because AV is GMRD, right? So having large voltage gain, that results in lower noise. And on top of that, if you want to have a lower flicker noise, then WL area must be also large, right? So how we can implement the lower noise? Based on that analysis, you can find a way to get the lower noise, right? So far we just only considered input reference noise voltage source shown here, but in some cases where input impedance is finite. For example, if we have a resistor and if we have a capacitor at the input, we have a impedance like 1 over SSD in typically. If that is the case, the situation becomes different. And for example, for this kind of amplifier, we calculate the input reference noise voltage source by tying input and measure the output noise voltage and divide by the voltage gain, right? Divide the output noise, the voltage gain. Then you will get the this kind of input reference noise voltage. In that case, we ignore the flicker noise. Now consider this model should represent real circuit. So if we add some input driver with the source impedance of R1, let's apply this and see the output noise voltage. If you, for example, if you have a like noiseless, if you consider like a noiseless this R1, we only consider like a circuit noise Vn square and Vn square in. Now let's monitor the output noise voltage. So in this case, input is tied to ground, and this one is a noise source. So we can swap the location of the voltage source and resistor. This is the same equivalent network. So we find the output noise voltage of this network. Then we have RC low pass filtering, and then common source amplifier. What we have is that input noise voltage time RC low pass filtering transfer function, and then the GM and RD voltage gain. If you equate those, what we get is the output noise voltage is like this. But this is not true. When you monitor the output noise voltage, we are not getting this things, because for example, if you tie that to ground, all the noise source coming out of the M1, right? So IN square, right? This noise source has nothing to do with the Cin and R1. If you assume that R1 is source impedance doesn't have any noise, because we lumped all the M1 into input referred noise voltage, that the output must be output voltage should be exactly same as this kind of a circuit network R1, and all the noise from the transistor IN1, and then noise from this resistor and transistor, right? That's M1 and IN R square M2. So if we end out, if you find the noise voltage at the output, it has nothing to do with this network CGS Cin. So it shouldn't be like this value. So infrared noise voltage has some error, right? It doesn't properly represent the circuit noise when we have a finite input impedance in the circuit and also non-zero source impedance like R1 shown here. So in this case, just voltage noise equivalent infrared noise voltage itself is not enough. So we have to consider current noise source, infrared current source. So we will see later in the next slide. So for any in general case, when we model the noise on the infrared noise source, we have to consider both noise voltage and also noise current, like this. In that way, any input impedance G in can be handled, right? If that has non-zero impedance, then just voltage noise source is not enough. So we have to consider both, like this network, right? Once we model this network, it should behave like the same. So we have, let's say, noisy circuit. Either we connect if we input to 0, tie to 0, we measure the noise, right? And also noisy, either you make it open, you also have the noise, right? This kind of a noise should be properly captured on the equivalent circuit here, equivalent circuit. And noise model must properly represent the above both case, the above case. Either input is open or let's write down input is shorted to GND, or input is open. In both cases, must have a same output noise voltage, right? So this kind of a voltage and current source must present. So if we N in and IN in must present it. Okay. So in this case, we will see what the voltage source and noise voltage and noise current behaves. For example, if for the noisy circuit we tie the input to 0, then we will see output. For the equivalent circuit, let's say we tie the input to noise voltage tied to ground here, right? Then what we have is in this noise voltage current will go circulate through this noise voltage, because this noise voltage has a zero impedance. This noise current doesn't do anything, doesn't affect on those two voltage at the input. Only the noise voltage source will affect the noise voltage by the KVL and KCL. What happens for the input open case? If the input is open, let's say here, equivalent model, if the input is open, you will get only this voltage source is hanging in the air. It doesn't affect the noise voltage. You will think of, you can treat that as infinite amount of resistor is connected there. So no current here, I equals 0. So this voltage doesn't affect on those input network. What affect is that this noise current will flow through input impedance of the circuit. That will create here, that will create the voltage drop, right? That affect the output. So for both cases, you will measure the output voltage. Those voltage must be matched, must be same, right? It will show some different value, but it must match to both cases. Therefore, this kind of a voltage and current noise input reference noise voltage and current properly represent actual noisy circuit, right? So going back to previous example, we were able to find the input reference noise voltage like that. Now let's find the input reference noise current. How we get this noise current? First, we make this input open, and all these noise current flow through Cin, right? All the input network. So we can find out the noise output voltage. Noise output voltage would be In square times input impedance square, right? And then GMRD circuit gain. So now we will get the overall VOKT, gamma GM plus VOKT over RD, and RD square is the this is the output noise voltage based on the input reference noise current. Now we can also find this output noise voltage a different way by having, let's say, just a input. Let the circuit open, just circuit equivalent. This must be equivalent to RD. Make this one open like this. For this kind of a network, what we measure at the output as a noise. For the noise, by the noise, we will see some output noise voltage variation. It's noise source coming out of resistor and transistor. we can calculate the output noise voltage easily by, since we have RD impedance, all the noise current density times RD square will be output noise. So the noise we found on the right hand side equivalent noisy circuit and the noise found by in the left hand side circuit based on input reference noise current must be equal, right? Using that fact, we can derive the IN input reference noise current, that is C in omega square for KT over GM square RGM plus gamma GM plus RD. So this is the final input reference noise current you can find, right? Based on those two circuits are equivalent, okay? Now we find that input reference noise voltage here, 1, and then also input reference noise current, 2. This only happen when we consider the finite input impedance Cin shown in here. What happens if we have if we assume that the Cin is 0, there is no impedance, so input impedance is infinity, then what we can consider is that Cin becomes 0 and input reference noise current becomes 0, right? So this one becomes 0 if Cin is 0, right? So if we don't consider Cin input impedance, then this input reference noise current becomes 0. So what we have in that case, we just take only take into account noise voltage source. That would be enough in that case, okay? Now we found that the proper way of representing noise of the amplifier is include both noise voltage and current. Now if something else in previous stage driving our stage with the source impedance of GS, let's calculate the X node voltage at the input. That would be what? Base X noise voltage influenced by this noise voltage and current. So in that case, Vnx node voltage would be what? Vn voltage will be divided. Voltage division will be resistor division take place. We can easily, this is equivalent to what? So changing noise voltage source, change the location would be same, the GS and Gin. First for the Vn square in, we can use the superposition. So use superposition. So second would be what? So GS and Gin, we have a current source there, right? For first network, we can find the X node voltage in here, like this, voltage division. And for the second equation, we have a current going through GS and Gin. So this is the impedance, total equivalent impedance, and current is flowing like that. So if you look at more carefully, the X node voltage is both affected by the noise voltage, input reference noise voltage, and input reference noise current. Now, if we have the same factor here, right? Same factor. So if the GS times IN is much smaller than noise voltage source, meaning GS is much smaller. GS is much small. Then the effect of the IN becomes if the GS impedance of the GS is much let's say what smaller, then the effect of the IN is negligible. So this condition kind of give us guideline when we consider the input reference noise voltage. So this equation can be written again like this. So source driving impedance is much smaller than Vin square over the IN input square. Then what? Input reference noise current can be negligible. So what would be the case? That would be the case is, let's say GS is equal to 0. For example, your driver is ideal driver. It has like an ideal voltage source. Then we can ignore the input reference noise current, right? So ideal voltage driver. We can ignore IN square, right? Okay, that would be okay.